Hey guys, I hope you're having a great week. I got a couple of requests to go through chapter 6 and 7 of logic that we didn't have time to do last week because of the science fair. So I'm going to do that without feedback from you on this video. I won't know if I'm going at a good pace or too fast or too slow. So you might have to rewind if I'm going too fast, or you could always skip ahead if I'm going too slow. I'll do a little bit of chapter 6 and a little bit of chapter 7 since I've had requests for both in the last day. So for chapter 6, the first thing to think about is that is defining some terms. Okay, so the first thing is logical equivalence, and logical equivalence means just what it sounds like. It means that two arguments are equal. Okay, so the symbol in math for equivalence, we all know, is of course equals. So I can say 3 equals 3, or A equals A, and that makes sense. So in logic, we use the biconditional operator that you've seen previously, and you can think of this as having 3 lines because you have if and only if. Okay, so I can do the same thing like I have here. So I could say A if and only if A. Okay, and then if A is false, A will be false. A is true, then A will be true. So that makes sense, I think. So this will be true and this will be true, or if A is false on this side, then A is going to be false on this side. Okay, you're going to have equivalent truth values, and this is what we're talking about when we say truth values. They're both going to be false, or they're both going to be true. Those are our truth values. It doesn't actually, at this point in time, matter exactly what the argument is. It just matters if one is true, then the other is always true. For example, I could say, let's see, what could I say? Without getting into a medical argument, I could say that if my heart is beating, if and only if my heart is beating, then I am alive. Okay? So if my heart is beating, that's true, then I am alive, that's true. The other alternative is my heart's not beating. Okay? So my heart's not beating, that's false, and I'm not alive. And it doesn't matter which way we go. Okay? So we could say that if I am alive, I am alive if and only if my heart is beating, okay? So I can reverse these terms, and it still works, okay? So again, if I'm alive if and only if my heart is beating. If that's not true, if I'm not alive, then my heart's not beating. And granted, we don't have to get into, brain dead arguments and things like that. You get the idea. Or how about another example would be, let's see, how about, well, I'll tell you what, let's go on to the next thing. All right, so that's logical equivalence. The next thing is a tautology, okay? So tautology is when two arguments are equivalent, when two arguments are always true due to their structure, okay? So I could say that either I am a man or I am not a man. Okay? That's always going to be true. Okay? It's like when someone says, well, either it is or it isn't. Either you're good or you're not good. Okay? We also think of this as good or bad. Okay? And you know what we could do here? Since these should be logically equivalent, we can say you're either good or not good, if and only if you're either good or you're bad. Okay? And we can combine these because if you look at these two terms, bad and not good, isn't that the same thing? You are not good if and only if you're bad. You're bad if and only if you're not good. Usually you'll see these tautologies in the simplest form when you have an or operator, okay? And especially if you negate one argument, so we have good and then we have not good being negated. Or over here we have good or bad. We have man or not man. What's another thing we could have done with man or not man? Well, we could have said that you're either man or woman. And we could have done that because, of course, if you're not man, then you're a woman. And I realize that in our modern day and age, this may not be so simple. But in the old days, you were either a man or a woman when you grew up. So that's a tautology. The opposite of a tautology is a self-contradiction. And the simplest form of that is if we simply change out the or operator from the previous example. So how about if I say, I'm a man, or I'm not a man. So that's the tautology with the or operator. It's always going to be true. If over here I turn this or into an and I say, I'm a man and I'm not a man, well, that obviously can't be true. That's a self-contradiction. Or what else? Can I say I am good and I am not good? Well, we kind of do say that, but we mean it differently. Like I'm good sometimes, but not good all the time. Or I'm good at some things, but not good at all things. But generally, if we say that you're a good person, then we can't also say you're a not good person. What else? So I wouldn't be able to say I'm a man, or excuse me, I'm not female, but W. I'm a man and I'm a woman. I can't say that. I can't say I'm a human and I'm a dog. Literally, I can't say that. Okay, so those are all self-contradictions. So there's three relationships that you could have when we think of this. You could have equivalence. Okay, so two arguments can be logically equivalent. They can be contradictory, or they can be neither. Okay, there's actually a middle ground with this. And let's see if we have an example of middle ground. I think we do later. Something else I want to point out again. So these are your three possibilities. For relationships. And plan ahead, obviously, when you're writing on the board. Between statements, arguments, I should say. Arguments. All right. Those are your three possibilities. They're equivalent, they're contradictory, or they're neither. They're something in between. All right. So that's most of chapter 6. There's one thing I think we might have covered it in a previous week, but I want to point it out again. So if you have, you guys see P, if P, then Q a lot in the book. I also like saying if antecedent, then consequent. Okay. But what I want us to go through is the truth, just a simple truth table for this, and I want to do that because you're going to see something. All right, so let's say the antecedent is true and the consequent is true. Let's say in this column that the antecedent is true and the consequent is false. And why don't we say here the antecedent is false and the consequent is true, and the antecedent is false and the consequent is false. All right, those are all of our possibilities, for truth values for argument A and argument C, antecedent and consequent. And what's interesting, and this is a crucial, important concept in logic, and without remembering it, you could get lost in the next chapter, We're going to make pink like red for false. Alright, there you go. Okay, so we've learned that for if-then statements, if the antecedent is true, the consequent must be true. This if-then operator is true. Here we have a true antecedent, but the consequent is false. The if-then is false. Okay? You guys remember we did this example. If I go to the beach, then I'll be happy. Okay? And let's say I went to the beach and I was happy. The if-then was true. Alright? Now let's say I went to the beach, but I'm not happy. That means the if-then wasn't true. If I said, if I go to the beach, then I'll be happy, but I go to the beach and I'm not happy, the if-then's not true. Alright, now here's the interesting part that's special in logic that I want you to pay particular attention to. It's this section here, okay? And the reason is that if the antecedent is false, it doesn't matter if the consequent is true or false. That's what you're seeing here. And both of these are true. And essentially what we're saying is, if you don't have the antecedent, then you're going to presume the if-then is true. And it doesn't matter if the consequence is true or false. So if we go back to the beach example, you know, there's more than one way for me to be happy. If I go to the beach, I'll be happy. But let's say I get all my work done and I do a good job. That'll make me happy. Let's say all my Challenge B students do their homework. That'll make me happy. So there's more than one way for me to be happy. There's also more than one way for me to be unhappy. Let's say none of my Challenge B students do their homework. Well, that would make me unhappy. Or let's say all of my kids are bad. Well, that would make me unhappy. So there's more than one way for me to be happy, and there's more than one way for me to be unhappy. What's important is that we presume the if-then to be true if the conditional is false. The only way for this to be false is if you have the condition but you don't get the result. Okay, so anyway, if you have questions about that more, let me know on Thursday, and we can go through it again. Now this gets important in the next chapter, and without remembering this, one of the first introductions to the concepts in the next chapter seems really confusing. Okay, so just remember that. Well, I'll do it again. If I say, if I do all my homework, I will get an A on the test, and I do all my homework and I get an A, then it's true. Let's say I did all my homework and I got a B, or not an A, then it's false. Okay, and then let's say I didn't do my homework, well then we have no idea what's going to happen, it doesn't matter. Anyway, there's another example. Okay, maybe we should do one of the exercises from 6 before we go to 7. Yeah, we'll just do, how about number 1? And what we're going to do here is determine if this set of arguments is logically equivalent, contradictory, or neither. Okay? Let me write it out here. So we have not P or Q. There's one of our arguments. And it is, looks like I had more space. I could have spread this out some more. So when you're trying to determine if two arguments are logically equivalent, you always set them equal to each other, logically equivalent, using the biconditional. So we have not P or not Q. And I have some more room here so I can spread this out a little bit. Not P or Q. Okay, so one of the key rules to remember is if we set an argument in any, we're going to do rows of this, guys, and in any particular row, if we set an argument to be true, then that same letter has to be true everywhere else through the row, okay? So why don't we just start and make P true. So you start with the individual arguments before you work on the operators. Once you start working on the operators, you work from the middle out, okay? So we're going to make P true. P is going to have to be true, all right? We're going to make Q true, and we're going to make Q true, okay? Now we can start working on our operators, okay? What do we know? First thing, let's work on these negations, okay? We know that if P is true, not P, must be false. If Q is true, not Q, must be false. All right, great. So what do we know about OR operators? If one of the arguments is true, then the OR operator is true. In this case, we have both true. The OR operator is true. In this case, we have both false, so the OR operator must be false, okay? And, all right, so here's our final argument. You can drop this down if you want. It's false, okay? I don't know if it's easier to represent it that way or not. Maybe I'll just draw an arrow. It's false. Over here, this operator was true, but this whole thing is negated, so the whole thing is false, okay? So let's see, what do we have now? Well, that should be correct. The operator is, well, they're logically equivalent for both false. So that should be true, but I think that's wrong. Let's see what the book says. No, the book says that we're right. We're correct, guys. The book says we're correct. And I'm gonna run out of room if I keep doing it this way. So I'm gonna put these back up here, guys, to make more room. Okay. I'm just gonna erase where I was dropping that down. All right. So what you see, guys, false and false means my biconditional is true. All right. Let's try another example. How about we leave P true? All right, P is true here. P is true here. Now let's make Q false. Q is false. Q is false, okay? So same deal, we're going to work on our order of operations, okay? We're going to cover negation first. If P is true, the negation must be false. If Q is false, the negation must be true. Remember, negations always have opposite truth values of whatever it is they're negating. All right? Now, we can keep working here. We have false and true. Because it's an OR operator and we have one true, the OR is true. All right, over here we have true and false. We have an OR operator. Since one is true, it's true. But we're negating this whole thing with the OR operator. So again, this one is false. All right, so we have false and true. The truth values don't match. So it's not biconditional in this row. All right, so what else can we do here? We can make P false and Q true. So if we do that, let's see, then P needs to be false over here. Since it's false there, it's false there. Q is true here, so Q has to be true over here. And now we can start working on it. Let's do the negation first. All right, so this is false. Negation is true. Q is true. Negation is false. Again, we have one true. This one's false. This one's true. Since we have one true, the OR is true. Let's work on this side. We have one true on our OR, so the OR is true. The true OR gets negated. So this is, again, false. Let's see what we get. We have false and true. So in this case, the biconditional is false. All right, let's work on our last possibility. We'll make P false and and Q false. So again, we can't change the truth value of the letter in the row, so they're all false. Now let's do our negations. False P means negation's true. False Q means negation's true. Let's work on our OR. We have true and true, so the OR must be true. Over here we have false and false, so the OR must be false. Two falses on the OR gets us a false. Alright, now let's see, we have to negate the false, so that's true. Now let's see what we have. We have a true and a true. True. Alright, so in this case, the answer is, so we have three choices. We have logically equivalent, we have contradictory, and we have neither. Okay, because we have true and false values on the biconditional, this is a neither. On before E, is it like that? Spelling. Let's see. Yes, I spelled it right. Great. Okay, so this is neither. All right. I'm going to erase this. You might want to pause it before I go on, and I'm only going to erase part of it. Okay. All right, so there's a couple of other things that could have happened with the biconditional. All right, if we get all trues in the rows, like let's say we had other arguments, and you always have the biconditional in the middle, but let's say we got true, 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 and true. Well, then in that case, these would be logically equivalent. Okay, so if you get all trues on your center row, between the two sides of the biconditional, you get all trues, it's equivalent. All right. The other thing that could have happened is we could have gotten all falses. And you guessed it, in this case, this would have been contradictory. Okay, so as you go through the exercises in lesson 6, that's what you're looking for. Is your central biconditional column, what are the truth values? All true means equivalent. If you have a mix, it's neither. And all false is contradictory. Okay, so I think that's it for chapter 6. Work on those problems. If you need help with any of them, we can talk about them on Thursday. Let's go on to 7, which is an extension of these ideas. Let's see. All right, so remember from the last chapter, we said that if the premises are true, then the conclusion must be true. That's what makes for a valid argument. And you'll remember that if you look at the chart on page 40 and you look at the if-then, the top left of that chart, you'll notice the only time the if-then is false is when you have a true premise and a false conclusion. Okay, so that's what makes an invalid statement, and that's why they show that. And guys, you remember from studying over the break that this symbol means therefore. We're going to use that more coming up. What else is important? As we make truth tables, if we can make one single row that's not valid, that means the entire argument is invalid, okay? And that's what this chapter is about. It's about using these truth tables like we've been making with trues and falses going down, whether or not they are true and whether or not your argument is invalid. If you have one invalid row, it's not valid. It doesn't matter if every other row was valid, okay? The key is to look for a row with all true premises and a false conclusion. And we're going to go through the table on page 44, which may initially be confusing, okay? So let me just recreate it for you first. And, let's see. Don't need that or. All right, so we have if P, then Q, and we're going to say not P, and then we're going to say therefore not Q. And let's go ahead and build this out. We're going to have, all right, so remember the chart back on page 40 in the top left with the if-then. You remember an if-then is true, has 3 true rows and only 1 false row, okay? And you may say, well, why is that? And well, guys, remember, if the premise is true and the conclusion is true, then your if-then is true. If your premise is false, we presume that the if-then is true, and we don't care if the consequent is true or false. We don't care if it's true. We're just going to presume it. I stressed that in the last exercise because of this. Where you get an invalid, what you can't have is a true premise and a false consequent. If you get that, then the if-then is false. And we're going to kind of test that with this table, okay? Now the book has left out this column and this column on purpose to try to help you grow and go on. But let's go ahead and see what we can do here, all right? So if we say P is true here, well, it has to be true here. It's true here, has to be true here. P is false, so we have to make it false here. P is false, we have to make it false here, all right? Same thing up with Q, all right? So Q is true, well, it must be true here. Q is false, must be false here. Q is true, must be true here. Q is false, must be false here, all right? So let's go ahead and do what we can do next, which is to work our negations. Negation is always the opposite of the argument, all right? So true premise means the negation's false. It's false here, it must be true here. Same thing here. False, true, false, true. Okay, so we've worked that out. Now what I'm going to do is erase the extra columns that essentially have showed our work to make this look like the book, all right? So we're going to just simplify this because we're becoming advanced in logic. We're going to clear out our work and see what we're left with. Okay, so remember the definition. I should write this down. The definition of an invalid argument is an argument that has true premises, all true premises, and a false conclusion. Okay, that's the key here. Okay, so we have 2 premises. This is one premise, and here's our other premise. All right, and what we need to look for is our rows that have all true premises. All right, and if we look, we have this row has all true premises. Okay, true, true, all true premises, and this row has all true premises. True, true. All right. Now the key to solving this table is noting that we have a row that has all true premises, but a false, so here's our conclusion, a false conclusion, okay? And that's why you see the book has identified this row as the key to determining that this is an invalid argument, okay? In your exercises, and I'm running out of time, I have to go, but when you do your exercises, if all of the rows with true premises have true conclusions, then that means that the argument is valid. Okay? And that's what you're doing in chapter 7, is you're determining whether an argument or a series of arguments, the way they're constructed, is it valid or is it invalid? And the key is looking for rows with all true premises, like this row. Whoops, that's not where I should have drawn that. The key is to looking for rows like this row and this row, okay? And you know what? These rows don't matter. They don't tell us anything. Not a thing, because we need to have all true premises and a false conclusion to determine validity for an argument. And remember, if you have one row that's invalid, it doesn't matter if you have other rows that are valid. Anyway, guys, I think that's it. You're going to work on some of those in just the same way in the exercises. If you have problems with any of them, bring them with you on Thursday, and we'll work through them before going through chapters 8 and 9 for next week. So, anyway, guys, hope you have a good rest of the day and week, and I'll look forward to seeing you Thursday. Bye.